So this talk is about some joint work with Damien Gaboriau about subgroup spaces, which we've heard a little bit about this week, but the basic idea is very natural. If we want to understand a group, it's natural to want to understand its subgroups. So there are various properties we might be interested in. Is it simple, residually finite? How many subgroups does it have? And we'll see that a lot of these properties have topological consequences when we view the space of subgroups as a whole. So let me start with some notation. So throughout, I'll denote by G a countable group, and it will usually be finitely generated. And by sub G, I mean the set of all subgroups of G. This is a subset of the power set of G, which we can identify in the usual way with the set of functions from G into 0, 1, which equipped with the product topology is a Cantor set. And it's not hard to see that sub G is actually a closed subspace, which means it inherits some rather nice properties. In particular, it's a compact Polish space. Right, so as you can probably see from the title, the object that interests us mostly with this space is what the perfect kernel is, so what the largest perfect subspace of the subgroup space is. And this is well defined due to a theorem of Cantor-Bendixson, which tells us that any Polish space has this unique decomposition. So for sub G, it decomposes as a perfect space K of G, which we call the perfect kernel, and a countable set C. So perfect just means it's closed and it has no isolated points. Okay, and one more thing before I go on to an example. The basis that I'll be referring to is defined as follows. So if you take two finite subsets I and O of G, then we denote by V of I and O the set of all subgroups of G which contain I and omit O. And the set of all these subsets forms a basis for the topology on sub G. So let's start with an easy example. What happens if you take G to be the integers? Well, we know what the subgroups of the integers are. They're all of the form n times z, where n is either natural number or 0. There are two obvious cases to consider. First of all, if n is not equal to 0, then nz is a finite index subgroup, and it turns out that if you just take the basic open set, which is all the subgroups which contain n but don't contain everything before it, so 1 through to n minus 1, the only subgroup of the integers which verifies both of these properties is nz itself. So it's isolated. And the last case to consider is what happens when n is equal to 0. So it's the trivial set. Okay, which is actually equal to the intersection of all the other subgroups. So it turns out if you just take the limit of nz as n tends to infinity, then you get this back. and it's not isolated. So what this space looks like is you have one point, the trivial subgroup, which is approximated by every other subgroup of the integers, each of which is isolated. This is homeomorphic to the one-point compactification of the natural numbers. And clearly here, the perfect kernel is empty because there's no perfect subspace. Okay, now, if we take maybe a higher rank free abelian group, it's a little bit more complicated, but not very much. What happens is that any subgroup is a free abelian group of rank, say at most D, and the subgroups of maximal rank are isolated. The subgroups of rank, say D minus 1, can be approximated with isolated subgroups, but if you remove those, then they become isolated. So we have this sort of decomposition of the space. And the perfect kernel is still empty. For finitely generated abelian groups in general, it's not very much more complicated, but there are some interesting things to say about countable abelian groups, and these were classified by Cornulier, Guichot, and Beach. Guyot, sorry. And in terms of these perfect kernels, they were found for a number of groups. In particular, there's a result by Bowen, Grigorchuk, and Kravchenko. They found what the perfect kernel was for the Lamplighter groups. So if you take a slightly generalized Lamplighter, its perfect kernel is actually all the subgroups that are contained in the normal factor in the semi-direct product. So and some other results to point out. There's a result by Skipper and Vizvedek. So they found these for a number of branch groups, including the Grigorchuk group and the Gupta-Setki 3 group. And lastly, we heard a little bit from Alessandro earlier this week, and in fact with Gaboriau, Lemaitre, and Stadler, they found all the perfect kernels of the Bomslag-Solitar groups. Okay, so before I tell you anything new, let's make just some initial easy observations. First of all, if my group G contains a subgroup which is not finitely generated, then this subgroup is not isolated. And the reason why is that you can approximate it from the inside using its own subgroups. So if you just take a countable generating set for H, then the limit of larger and larger, well, the group generated by larger and larger subsets of this generating set converges towards H. This doesn't necessarily mean that it's in the perfect kernel, because you need to actually find a perfect subspace for this with the subspace topology, but it's a first step. Conversely, if you have a subgroup which is finitely generated, then you can't do this, because the set of all subgroups which contains it is itself an open neighborhood. So any finitely generated subgroup, you're going to have to approximate it from the outside. This creates an initial problem if your group is finitely generated and you take a finite index subgroup, then this isn't possible anymore. There's just not enough on the outside. So it turns out you can explicitly, using basically the same method as for Z, you can show that it's an isolated point. So this raises an initial question, which is, if I give you G a finitely generated group, well, straight away we know that its perfect kernel is necessarily contained in the set of infinite index subgroups. Which I'll denote like this. Okay, so the initial question is, well, fine, when is this inequality an equality? So when is the perfect kernel as large as it possibly can be? And the first example that I heard about of this is something that is quite well known, I think. And this is for finite rank non-abelian free groups. So this is true, and there's a proof of it in a paper by Carderi, Gaboriau, and Lemaitre as well. And so what Damien and I wanted to do was find more examples of this behavior and maybe see where things get a little bit more complicated than this. And perhaps one of the very natural places to look for this is to have a look at surface groups. And it turns out that as long as you make the reasonable assumption that these are hyperbolic, then this is once again true. These arrows denote train of thought and have no mathematical meaning, to be clear. So once you know that something is true for surface groups, the next question possibly might be, what about limit groups? And again, if we make the assumption that they're non-abelian, then this once again holds. Now, an equally valid way, well, place to go from surface groups is to think about higher dimensional manifolds. So in particular, we were interested in hyperbolic three-manifold groups. And it turns out that the situation here becomes more complicated. And in particular, this inequality doesn't hold. And I just want to tell you why quickly. Okay, so the thing about hyperbolic three-manifolds is that quite a lot of them are fibered. So specifically, they fiber over the circle, and the fiber is a surface. And what this means in terms of groups is that if you look at the fundamental group of a fibered manifold M, well, it projects onto the integers, and the kernel is a surface group. In particular, maybe not use K. In particular, it's finitely generated. And, we know that the set of subgroups of pi1 of M that contains H is in bijection with the quotient. So, standard thing to do. Well, the subgroups of the quotient. So this is actually, on its own, enough to conclude that H is not in the perfect kernel. The reason why is, as I said before, the fact that H is finitely generated means that this set is an open neighborhood of H. And if it's in bijection with sub Z, it means there are only countably many subgroups in this set, and that's not enough. But we can actually say something a little bit more concrete, which is that this bijection is actually a homeomorphism. And in this context, it adds a little bit more information, not a huge amount, but in general, this is actually quite a nice way of building examples of things, because it means if you have this kind of short exact sequence and you put something interesting in the quotient, then you can lift interesting behavior to the subgroup space of the ambient group. Right, but in this case, what this tells us is that we've found H, a subgroup of pi1 of M, which has infinite index, but it's not in a perfect kernel. So that equality does not hold. Okay, and not all hyperbolic three-manifolds are actually fibered, but it was quite a big result from the last decade that every hyperbolic manifold is virtually fibered. So this is due to Hegel. And it turns out that, as you might expect, having this short exact sequence in a finite index subgroup is, again, enough to show that the kernel will not be in the perfect, yes, the kernel will not be in the perfect kernel. So that equality really doesn't hold in full generality. Okay, so we'll be able to say something a little bit more precise about this, but I'll get back to that in a second. Because first of all, this is not the only way, well, this is not the only place to look once you know that something holds for free groups. And another perfectly reasonable thing to do is to think about free products. And it turns out that it does work for these as well. Now, in the language of Bass-Serre theory, a free product is just a group which acts non-trivially on a tree, and the edge stabilizers are trivial. So what about groups that act with finite edge stabilizers, otherwise known as infinitely ended groups by Stalling's theorem? And once again, we can generalize this statement to them, so their perfect kernels are also maximal. And lastly, another interesting kind of action on a tree is one where instead of requiring that individual edge stabilizers be finite, you ask that stabilizers of sufficiently long paths are finite. So these are known as acylindrical actions. And what we'll see is that you can say something about the perfect kernel of a group which acts in this way on a tree, but ultimately, you're going to need more information about the group itself. It's not going to tell you what you need to know about every single subgroup.
Are you just considering finitely generated groups? Like
Yes.
Sorry.
Yeah. That's all right. Exactly not what I said. Okay. So let's state some results. So the first theorem that I want to tell you about is this one, so with Borel. And I'm just going to state it, and I'll explain the assumptions that we make later. But if G is finitely generated, subgroup separable, and the first L2 Betti number is strictly positive, then it follows that its perfect kernel is equal to the set of infinite index subgroups. Okay, so the first condition here, subgroup separability, is one which tells you that every finitely generated subgroup of G is equal to an intersection of finite index subgroups. So this has a nice translation in terms of subgroup spaces, which is that G is subgroup separable if and only if the set of finite index subgroups is dense in sub G. So this was first noticed by Glasner, Mellaret, and Kittwerzer. And no, it's nice. However, it doesn't tell us anything about the perfect kernel. So we had the example of the integers earlier, and they're subgroup separable, and yet their perfect kernel is empty because we don't want to approximate subgroups with finite index subgroups. We want to approximate them with infinite index subgroups. However, if you add this condition here that the first L2 Betti number is positive, which, if you know what that means, great. Otherwise, all you need to know for this theorem is that this gives us the ability to relate the index of a finite index subgroup with its rank. And so this allows us to actually find the sequence of infinite index subgroups that we want. Okay, so what does this tell us concretely? Well, In general, both of these conditions are non-trivial to show, but they are also very interesting, and they've been studied by a lot of people, so it does tell us some things. In particular, so first of all, free groups were shown to be subgroup separable by Marshall Hall back in '49, and they also have positive first L2 Betti number, so that result does follow from there. Also, surface groups are subgroup separable. This was shown by Peter Scott, and they also have positive first L2 Betti number. So this gives us our first result. More generally, limit groups are subgroup separable. This was shown by Wilton, and when they are non-abelian, Pichot showed that they have positive first L2 Betti number. Okay, so that's some initial things. Now, next, you might have noticed that a lot of the groups on this board are hyperbolic, and we might want to say something a little bit more general about hyperbolic groups, but it turns out that there's a slight problem here, which is when you're looking at a hyperbolic group, this is a condition which is defined geometrically. It's sort of the main tool that you have to work with, and finitely generated groups in general don't have to respect the geometry of the group. And in fact, using a bit of these ideas up here, you can sort of make the situation in a hyperbolic group as complicated as you want it to, almost. However, we can say something about those groups which do respect the geometry of the group. So these are the quasi-convex subgroups, and it turns out that the perfect kernel always contains all of the infinite index quasi-convex subgroups. In particular, there is a nice class of hyperbolic groups where all of the finitely generated subgroups are quasi-convex, so these are known as locally quasi-convex. And in this case, so if G is non-elementary hyperbolic, and locally quasi-convex, then we do get back the statement that the perfect kernel is the set of infinite index subgroups. So some classes of groups which verify this condition include hyperbolic surface groups. It also includes certain one-related groups, certain hyperbolic Coxeter groups. So there's a lot of work by Wise, McGammon, and Fuschka on this. And one more thing that I wanted to point out that I think I forgot to say is I did promise some dynamics. And that's because there is a natural action on this set of, well, the subgroup space of a group by conjugation. And this action is continuous. We can look at what some of its topological properties are. Okay. And not only is it continuous, but actually there's decomposition here into the perfect kernel, and the countable subset is actually G invariant. So G doesn't only act on its subgroup space, it acts on its perfect kernel. And it turns out that over here, if we add the condition that G doesn't contain any non-trivial finite normal subgroups, then the action is topologically transitive. So apparently there is some debate as to what the correct definition of topologically transitive is. And this is one of those rare cases where I don't really have an opinion, so I'll follow my co-author on this one. Actually, I want to leave that up. What did I do? Right, so what do we mean by topologically transitive? Suppose G acts on X, a topological space, then the action is topologically transitive. So this holds if given two non-empty open subsets in X, you can always find an element G in your group such that the translate of U by G intersected with V is non-empty. Okay, and so there is one condition where this holds. Now, the kind of thing that we use to prove this theorem about, actually, before I tell you that, let me get back to hyperbolic three manifolds, because I did say we could say something a little bit more precise. And this is because, in spite of not being locally quasi-convex, finitely generated subgroups of hyperbolic three-manifold groups are well understood. And in particular, they're all either quasi-convex or they're virtually these virtual fiber subgroups. And so equipped with this information, we can show that we can show the following. So if M is a hyperbolic three-manifold, well, closed. I should say there should be a closed up there. The closed case is due to Hegel. The more general cases, well, the cusp cases wise, but anyway. Okay, so if M is a hyperbolic three-manifold, then its perfect kernel, well, the perfect kernel of its fundamental group is precisely the set of infinite index. So it's always infinite index groups, but it's a set of infinite index subgroups such that either H is quasi-convex or H is not finitely generated. Okay, and again, we do actually get a, so these don't have non-trivial finite normal subgroups, so we again have a topologically transitive action on the kernel. Okay, so our sort of main tool that we have for proving this is that in a hyperbolic group, given a infinite index quasi-convex subgroup, you have a huge amount of flexibility to build other infinite index quasi-convex subgroups that actually split as amalgamated free products over finite groups, such that the group that you started with is a free factor. So this is behavior that was originally observed by Gromov in his essay, and it's led to various combination theorems, including by Arshantseva, Gittik, and various generalizations to generalizations of hyperbolicity, including one about relatively hyperbolic groups by Martinez-Pedrosa, which it turns out can be useful even if your group is hyperbolic in and of itself. And when looking at actions on trees, it turns out that there's a kind of similar behavior that's going on. And what I mean by this is that, so, if I give you a group which is acting on T, a tree, and I assume that this action is minimal and irreducible, so these are just conditions that ensure that my action is interesting in some sense. It just means that, so minimal just means that G doesn't fix any proper subtree of T. Irreducible means that it doesn't fix a point, a line, or an end in the group, in the tree. And as soon as I verify these conditions, if I give you H in G such that, well, firstly, H is finitely generated, and the quotient of H under T is infinite, well, using a little bit of Bass-Serre theory, you can quickly see that the quotient can only have finitely many cycles because H is finitely generated. So this sort of looks like this core with some cycles in it, and it's infinite, so it has some branches coming off. And the fact that this core exists actually means that H fixes a proper subtree of T. And so it turns out that you can use this to build bigger subgroups that split as amalgamated free products, as long as you have some assumptions on the action on the tree, which I'll point out in a second. But yeah, so despite the fact that these methods are different and the context is different, the idea is somehow similar. It's that the subgroups we're able to say things about are the ones that fix either a convex or a quasi-convex subset of a nice space that we're interested in. What do I want? Okay, and so what we're able to say in general is that if you have G acting on a tree, and notice this is actually the only place I'm not really assuming that G is finitely generated. So if G is acting on a tree and the action is minimal and irreducible, right, and moreover, I assume that there exists two edges, F1 and F2 in T, such that the intersection of their stabilizers is finite. Then, if I satisfy these conditions, if H is a subgroup of G and the quotient is infinite, then we're able to show that H is actually a point in the perfect kernel of G.
What's irreducible in this context?
So it means the action doesn't fix a point in the tree, a line in the tree, or an end. But when the action is minimal, you can just think of this as all the vertices have degree. Okay, it depends how many orbits you have, but globally, if your vertices have degree at least 5 and the action is minimal, then it's also irreducible. Okay, so what does this tell us? Obviously, the issue here is that I can only say things about subgroups where the quotient is infinite. However, if I know that the action actually has the property that every edge stabilizer is finite, then it turns out that every infinite index subgroup has an infinite quotient. So by Stalling's theorem, this gives us the result for infinitely ended groups. Now, acylindrical actions, remember these are actions where the stabilizers of sufficiently long paths are finite. This is actually a stronger property than this one. Here we just require there's the stabilizer of a path, which is finite. And so this does tell us that if your group acts acylindrically, then all of the infinite quotients are in the perfect kernel. The trouble is that you can build actions where, well, you can build an acylindrical action of a finitely generated group such that the group contains an infinite index subgroup where the quotient is finite. And you can do this in such a way that the subgroup in question is in the perfect kernel. You can also do it in such a way that it isn't. So you're going to need more information about the group to conclude anything in general. Okay. No. Right, and I guess the last thing to point out is that if the kernel of this action is trivial, then we again have a topologically transitive action. So this action is topologically transitive on the set of subgroups which verify this, which in the case of infinitely ended groups is actually the perfect kernel. And that's everything. Thank you.